We started with a problem in which we had 4 parameters. I remind you it was the temperature of the star, temperature of the disk, the beta exponent of the modified black-body law, and the F factor. When we tried to compute the values of the likelihood for a range, a grid of parameters, I actually, Python code was setting up a grid where we had 100 nodes in each axis. So we tested the likelihood at 100 values of the stellar temperature, 100 values of the disk temperature, 100 values of beta, and 100 values of F. Altogether, that means 10 times 8, right? 10 raised to the power of 8 grid nodes. Because our model is relatively simple, we could do that in less than a minute in a good laptop, okay? So, but still, it was quite a bit of computation. Now, I've introduced, I think it was 5 different groupings in the data. So I'm assuming that my stellar energy distribution is made up of data coming from 5 sources. It could be SDSS, WISE, whatever, Herschel, okay? So I've introduced 5 more parameters. 4 if we consider that the mean of them is 0. Let's assume it's 5. 1 offset for each data set. So we now have 9 parameters, and our grid will be 9-dimensional. If we still keep 100 points per axis, that would mean 10 raised to the power of 18 grid nodes. That is intractable. You just cannot do it, right? But also, even if you could do it, the outcome would probably be unsatisfactory. Simply because, a priori, you don't know how is your likelihood distributed. We may have a very narrow peak somewhere, okay, and our grid node would be very coarse there. It would be, imagine, I'm just simplifying in 2 dimensions, but maybe the grid points when I'm evaluating the likelihood, or the posterior, maybe something like this, okay? But it turns out that my likelihood is very narrowly peaked here. So I may miss this maximum simply because the values at the grid nodes are 0, it's very small there. Or even if I still can detect that there is a peak here, I will only be able to give values here unless I interpolate. On the other hand, the rest of the grid may have values of the likelihood which are completely negligible. So it would be this 10 to the 18 evaluation of the likelihood may be very, very, very inefficient. Okay, if I do this in a regular grid, I will be computing my likelihood in very many points where this is negligible, and I may actually be missing the points where the likelihood is significant. So doing it in a grid has its problems, its caveats. So this is in a 2-dimensional, but just think of 9 dimensions that we now have with the offsets. So we have to find a way to evaluate our probability distribution, the posterior probability distribution that I was talking about before the break, in a different way, which is more efficient. I would actually want to obtain the posterior probability there where it's significant. Wherever it's 0, I don't want it. I don't need it. Okay? And that's exactly what the MCNC methods do. So if you have ever wondered what's all this MCNC mess about, it's just a technical solution to the problem of trying to evaluate the posterior probability in a sensible way, without wasting computation time. Okay? It's nothing more than that. We could actually have solved this problem to infer the parameters of our disk together with the offsets using the grid. Okay? But I prefer to actually use this MC-MC sampling to illustrate the use of MC-MC techniques. Okay? So I will try to solve this problem just using exactly the same formalism as before. I will define a likelihood, I will define a prior, I will multiply the two to get the posterior, but instead of obtaining the posterior everywhere in a regular grid, I will let Python to generate a bunch of points, a bunch of parameters, which are supposed to be sampled from the posterior distribution. Okay? So I will not have an analytic posterior. I will not have my posterior evaluated at a set of grid nodes. What I will have is a set of points, the density of which is proportional to their posterior probability. This is the outcome of one of these Markov chains. Okay? So from here, you can get something analytical just by doing a kernel density estimate, for example. Okay? You can put a Gaussian in each point, sum them all, and if you're clever enough in choosing your kernel size, then you have an analytic, something you can actually evaluate at any point. Okay? So what I was doing here in the next Python code is actually to generate an SED, spectral energy distribution, affected by the offsets. Okay? So I create an SED above, and then I generate a field. If I have like, just like explaining so that you understand what we are doing, if I have 15 measurements in my SED, I generate some random numbers between 1 and 5. Imagine it's 1, 3, 7, 11, and I say 14. Everything between observation 1 and 3 belongs to the data set 1. Everything between 3 and 7, data set 2. Between 7 and 11, it's data set 3, and so on. Okay? So this is just an artificial way to define data sets. And then for each one of them, I generate an offset from a random distribution, which is, where are the offsets? Yeah. It's the second line here. Offsets are drawn from a normal distribution centered at 0 and with a standard deviation of 1 times 10 to the minus 12. It's very small, but recall that we are in a logarithmic scale and the fluxes are more or less of that order of magnitude. Okay, so that's more or less, it's a bit smaller than, I think it's 1 order of magnitude smaller of a typical value in the SED. Okay. So I add those offsets to the original SED. That's what I do here in this line. So for data set 5, I get the original SED and I add an offset. Okay? It's very simple. If you look, unfortunately the color code is not well chosen. But here you can find points in blue and black. And the difference between the SED and the displaced offset SED are reasonably small. Okay. Now, you already know the likelihood without offsets. Now, the likelihood with offsets is a little bit different. Okay? This would be the likelihood for my model. And in this model, I've actually introduced what I call here nuisance. Is exactly the same as offsets. Okay? I call them nuisance to emphasize the fact that I'm not interested at all in knowing the actual offset. What I'm interested in is in the physical parameters of the star plus disk. And I will actually integrate over these nuisance parameters. So the probability I now have a likelihood for my data given my parameters. And my parameters now are T star, T disk, beta or beta, F, and the offsets. Okay? What would be my likelihood? I think this would be a nice exercise if you try to derive this likelihood. Before, we had a likelihood which was a normal distribution centered at mean with a covariant matrix. The covariant matrix was diagonal. And the mean was the fluxes given by my black body. Okay? So this was the black body at T star, function of these, and then the modified black body at T disk with beta times A, where A was a function of F. Okay? Now, what would be now my likelihood? Now, this is not enough anymore, because I have more parameters, right? The other parameters are the offsets. And these offsets are actually entering my likelihood here. Now the mean value for a given observation would be the value given by the model, blackbody model, plus or minus, I've written there minus, the offset for that observation. I know that I will not be observing the real value of the star. It will be something above or below simply because when I calibrated my instrument, I introduced this offset. Okay? So if you put here plus, the offset will come out as the opposite side. There's a choice here. You can put plus or minus. And that's not log likelihood. I'm not going to use this Python code because I would have to evaluate this likelihood, or equivalently the posterior, in a grid, in a 9-dimensional grid. So what I will be doing is actually use the next block of Python code, which is the way we do MCMC with the stun. Okay, it's difficult to get into the details, but still I want to give you an idea of what this is, right? Again, stun is based on Hamiltonian Monte Carlo. If you recall the hands-on exercise that was proposed by Jake yesterday, in Markov chain Monte Carlo methods, you have to have a proposal density. You propose a jump in your chain, and depending on the value of the likelihood at the ending point of your jump, you accept it or reject it. If you propose if your proposal distribution is such that most of your jumps are rejected, you're wasting an awful lot of time and computation effort. Okay? So the idea behind Hamiltonian dynamics is to try to come up with a proposal for your jump that favors points that will be accepted in the end. Okay? So that's the rationale behind Hamiltonian dynamics. And it's very interesting because if you recall from the statistical lessons that we learned when we were graduate students, we knew that there was a connection between the laws of motions of particles in a gas and the probability distributions for their velocities when they are thermalized. If you recall this, you end up finding the Boltzmann distribution for some assumptions on the dynamics, inelastic collisions, inelastic collisions, and so on and so forth. And there was an intuitive meaning for temperature. So what they do in Hamiltonian dynamics is just the same. We want to end up with a distribution. It's not the Boltzmann distribution, it's the posterior distribution. So let's define a Hamiltonian that allows us to end up with this distribution. Okay? I will not go into many more details, but basically in the simplest case there's always subtleties everywhere, but here we define in the first block, which is named data, we define actually the input to the sampler. Okay, so in this case, I'm telling the sampler how many observations make up the SED, which is the variable J. I tell the sampler at what wavelengths was the SED observed. That's flux underscore OBS. Those are the fluxes that I actually measure. The lambdas at which these measurements take place is lambda underscore OBS. The uncertainties in the fluxes, again, I am assuming that my covariance matrix is diagonal, but this would perfectly well work with a non-diagonal matrix. Then the number of datasets that make up my SED. Remember that my wavelengths are grouped according to the instrument that actually carried out the measurements. And then the actual dataset label. So this is the vector dataset. It has 1, 1, 1, meaning that the first three observations come from dataset 1, then 2, 2, 2, 2. Okay? So it's only the way I go. But this is the input to the sampler. Then I have transformed data, which is basically the place where you put constants. And you can see there, I have the speed of light, Boltzmann constant, the Planck constant, and then I have real plus 5, because I'm normalizing my SED so that my models, the black bodies, match the actual units of the observed SED that Alvaro provided me. So everything has to be around 10 to the minus 10, 10 to the minus 11. Okay? Then the next block is parameters. And here is where I define theta, the parameters I want to infer. And you can see there you have temperature of the star, and I help a little bit the sampler by saying that if it comes up with a proposal which is below 2000 or above 8000, it should be automatically rejected without ever calculating the likelihood, but this is just helping. Then the temperature of the disk, then the exponent beta, f, and then the offsets. Okay? So those are the parameters of my model. Then the block transform parameters is commented out, it's empty. And then the block model is exactly where I define priors and likelihoods. And now the sampler has almost everything it needs to start. I've given the sampler the observations, the fluxes, the lambdas, the number of datasets, etc. If I provide here the likelihood and the prior, then it's ready to go. So let me skip the definition of variables. Okay, so the first block is where I define, just like in Fortran or C or any other programming language, I define the variables. And then the first thing I do here is I define the priors. Okay, these 4 lines are defining the priors that my sampler will use. And the priors are the simplest one I can use. It's a uniform distribution between 2000 and 8000, uniform in the temperature of the disk, uniform in beta, and this is arguably a bad decision. And this was part of the things I wanted you to test. And then uniform in F. This is also, I think, a bad decision, because this is a scale parameter, and I think we would be better off with an exponential decay. Okay? So I've restricted here the range of values that F can take to a very narrow range, going from 10 to the minus 3 to 10 to the minus 2. And one of the exercises I would like to propose you, if if Python were running on all laptops, was actually to do a sensitivity analysis, to analyze the posterior resulting from these priors, and priors which would be different. We could use Jeffrey's prior for beta or F. I think that one would be at least one to be tested. Okay. You can see some commented lines just in case you want to look at the chains, at the actual values that the chains is testing, and then I have a loop going from 1 to j, and I remind you j is the number of flux measurements in our SED. So for each value in my SED, I'm going to compute the likelihood. Okay? So I wonder if the sampling on the offsets, yeah, it's below. Okay, I could have defined the offset, the sampling prior for the offsets there, but it's done later. Doesn't matter. So for each point here, for each point in my SED, I'm going to compute the black body for the star, the modified black body for the disk. I'm going to scale them with the F factor, just as we did before. There's nothing new here. And I'm going to compute the value of the flux that would be obtained for a given set of values of the vectors. Okay? And what I do afterwards, so here, here I'm actually defining the prior for the offsets. It comes from a multivariate normal distribution centered at 0 with a given sigma. And this sigma is a matrix which I define here. It's diagonal, it's 0 everywhere, except in the diagonal, where I've put a variance of 1 times 10 to the minus 6. Okay, the variance is the square of the standard deviation. Okay, so that fits my definition of both. I'm fixing here the value of the sigma of the offsets. And this is a guess. Well, of course, it's not a guess. I know where they come from, so I'm fixing the right value. These will translate in the fact that my Markov chains will quickly converge to the right solution. Right? I could actually put a prior on this thing here. And I'll come back to this later. Let me draw a diagram of my likelihood model. Sometimes these diagrams are very useful for understanding the statistical model you're using. I find them especially useful. So in this case, it's rather simple. We have here, down here, some fluxes. These are my observations. And these observations in my model, they come from the real fluxes of the star, but they are affected by some random noise. Okay? And these fluxes, I model them as depending on T star, T disk, beta, and F. That was my previous model with no offset. Okay? That's how I work. So this one was fixed for me. I put a double circle here because those are the uncertainties in the observation. I get them from the instrument model. And these are my parameters. So I had to put a prior probability on each one of them. Now, my observations do not respond to this model anymore. Well, but to an extended version of this model, where the actual fluxes do also depend on the offsets. Okay? Okay? So in order to get my observations, we have all these, and I've set a prior on the offsets. My prior on the offsets is a normal distribution centered at 0 and with a variance of 10 to the minus 6. Okay? I could actually, but I won't here, I'll do it later in another example. I could actually not fix this 0 and 10 to the minus 6, but I could actually think of this as another parameter in my model. I think that this comes from a Gaussian with a mean and a variance, and put a prior on the mean, put a prior on the variance, and infer them as part of my model. Okay? I could actually do that. Or, even better, in my opinion, I could actually not take this as granted, but actually infer them. Let's think I do not trust the uncertainties provided to me by the Herschel team. I think they did a poor job in calibrating the instrument, and I think they underestimated their uncertainties. So I'm going to consider this as yet another parameter of my model. I do not know the uncertainties. I'm going to try to infer their uncertainties. So I would actually use this as a parameter, define it in my model, and write a prior on the uncertainties. I could also do that. So when you have several levels in your model, that's what we call hierarchical model. We have parameters that have priors, and these priors in turn have parameters with their own priors. So we have hyper priors. Okay? And I will give you a good example of how this works right after this one. I think a useful one. So in this case, forget about this. We consider our uncertainties are correct, but I'm going to, and again, there is no hyper prior for the offsets. I just think I'm right with a mean of 0 and an epsilon of 10 to the minus 6. Okay? Well, having done all this, here's what I tell them. I write it like this. My observations are expected to come, this is the tilde here, are expected to come from a multivariate normal centered at the values predicted by the model, which I previously modified to take into account the offsets. Okay? So in the end, it's just exactly the same as before when we didn't have offsets, only that my flux model, or the fluxes coming from the model, have been offset by some random number. Okay? So for those of you who can actually run this piece of code, all of that was Stan code, and it is actually translated into C++ by PyStan, because Stan is C++ software. Okay? So all my specification of the model is actually translated into some piece of code which is run in C++ by the kernel of the system. And what I do afterwards is I define an initial point for my chain. Okay? This is not compulsory. You can actually let Stan grab an initial point randomly. The only difference is it may take longer to converge. Actually, the initial point is not the solution. We should be at 3,200, 120, 0.8, and 0.005. But we are not too far. So I wanted to make sure that you could run these within a few minutes at most. Okay? So that's the initial. Here I write, I think, how do you call this in Python? Is it a list or broken? A dictionary, right, a dictionary. So I define a dictionary where I say J is the number of wavelengths that I measure. The variable flux ops is filled in with this vector, etc. So this is the data I have to give the sampler, okay, my observations, my wavelengths, the number of data sets, which point belong to which data set, and then the next line is actually calling stan. Here is where I call stan this line. I say model underscore code is the model with offsets, which is what I defined above. All the blocks for data, transform data, parameters, and the model. These are the data which I've just defined here. I tell stan to create 4 chains, and each chain will actually produce 500 samples. Okay? And this is the initial value. In reality, if you read about Markov chains, there is a period, you start sampling from your initial point, and there is a period where your distribution does not respond to the posterior probability. It takes a time before the samples that you actually obtain are representative of your posterior distribution. It's usually called the burning phase. Okay? And those points where we expect not to have something representative of the posterior are thrown away. So in this case, if I produce 500 samples, 250 will be thrown away, okay? Because they may not be representative of the posterior. The second line, which is commented out, is for subsequent call to stan with the same model. So when you do this, you actually translate the model into C++ and compile it. The next time, if you try to run the same model with different data, you don't want to compile again the same model, because it's going to be the same binary object. The only thing that's changing is that you're applying it to a different SED. So here, instead of model code, model with offsets, which is what we defined above, you write fit, which is this variable. Okay? That way you don't have to compile again. If you have 4 chains, you have a way to check whether your chains have converged. In principle, if your chains have converged, they should be representative of the posterior distribution. And since the posterior distribution is 1, they should be the same. The chains, the 4 chains should produce the same posterior distribution. If you have 4 chains and they result in different posteriors, that's a strong indication that your chains did not converge. You're not dealing with a sample representative of your posterior. Okay? So that's something. There is always the necessity to evaluate, to diagnose your chains. You have to look at them. There are several ways in which you can diagnose your chains, but the most obvious, the most simple is that one. If the 4 of them give you different results for your posterior, then there's a problem there. Okay?
Why 4 chains?
There's always some room for discussion here. Why 4 and not 8? I don't have an answer. But I think 2 is dodgy. 4 begins to be sensible. The more, the better, of course. Okay. If you're absolutely certain that your change is going to converge, 1 is enough.
What is the burning?
Again, good question. By default, it takes just half, and I checked that this half was producing a good result. If you ask me why half, this is just some, I was going to say magic. It's not magic. The question here is, it depends on your proposal, right? And if your proposal quickly generates points which are all accepted, you're prone to explore only a very small region in the parameter space. Okay? On the other hand, if you allow your sampler to explore all parameter space and you allow for very long jumps, long jumps will probably end up in parameter values that are likely to be rejected. So most of your trials will be rejected. And 50% is sort of a compromise, yeah.
It's 50% if you've got ISO equals 1,000, you'd still throw away the first half.
Yeah.
And that would be the same as ISO equals 500.
Yeah, it wouldn't be the same. So it may happen that if your burning process takes only 100 or 200, if you go for 1,000, you would be throwing to the dustbin 300 points, which are actually representative of the posterior. There are diagnostics to. So if you continuously monitor your chains, as soon as you see your chains producing the same posterior, you can say, okay, I've converged. Anything from this point onwards is going to be accepted. So there are ways in which you can actually monitor your chains.
Does the Hamiltonian scheme have a different learning period to Tropic systems?
My experience is it does. My experience is it does.
Better.
Yeah. But probably it is also very dependent on the problem. For example, the example that Jay gave us yesterday, the MC hammer, my understanding is that that is a very good sampler when you have very correlated parameters. Is that correct, Jay?
Yeah.
So it's a thin invariant sampler, which means, yeah. So if your problem is one of these difficult problems to solve, then go NCMC. Go NCE hammer. Okay. I won't lie. It also has to do with how comfortable you feel with software suite or not. But it definitely has to do with the convergence speed. So in my experience, I have better results with standard. Now, this is the SED. I'm going to try to, it's again the same one as before, the one with the offsets. Now, once I run Python, what it would happen is that I will have stored in the variable feed the chains that I have produced with Python. Okay? So if I write feed.extract, it will actually store all the samples here into the MCMC variable. Okay? Feed is a compound. I do not know exactly the name of this kind of compounds. It's not a dictionary, it's a list probably, I don't know. Yeah, it's like a meatball with many things mixed together. And this is the way to extract information. Okay? Yeah. Sorry?
If we go into an ideal structure.
Oh, probably. Yeah. So now I'm storing the chains in these new variables. In T star, I have the values of the stellar temperature produced in each chain. Of course, the values are not produced independently. So what I get in these chains is kind of a matrix . So it's a matrix. Each row is a sample. Sample 1. And I have here T star, T disk, beta, F, and then offset 1 and to offset 5. So what I'm doing here is extracting this column. Okay? I can look at the marginal posterior, that is the probability for just one parameter, by plotting the values in the chains for that parameter. So this, for example, this thing here, is the posterior probability for the temperature of the disk. T disk given my data. This, the probability for different values of this temperature, if you recall marginalization, would be the probability, the posterior probability, T star, T disk, beta, F, and the vector of offsets. But in order to go from here to here, I have to do 1, 2, 3, 4, 5, 6, 7, 8 integrals. Okay? This is 9 parameters. Here's only 1, so I have to do 1, 2, down to 8, integrate in T star, beta, F, and the offsets. Okay? And this integration is automatically carried out, this integral. You can skip it because you're simply considering this value, this column here. It's exactly the same. Okay? This marginalization is equivalent to just looking at the column. There is a little trick here, which is here I'm not showing the samples themselves. I've constructed a probability density from the samples by using a kernel density estimate. How many of you think would need an explanation of what the kernel density estimate is? Okay. What happened here is I have 250 values of the temperature of the disk per chain. I have 4 chains, so I have 1,000 values. So for T disk, I have 1,000 values here. Okay? Now, if I do a histogram, what I'm doing here, I will obtain something like this. And this maximum is more or less at the right value of 120. This would be histogram. Okay? There are problems with histograms, so statisticians sometimes prefer to do this in a different way. Imagine I have these 1,000 values for the temperature of the disk, and at each point I put a Gaussian. So if this value here is 98, I go here, this is 120, I have one value at 98, I draw a Gaussian here, okay? And I do this for each and every value in my chain. And then add them up. The integral of this is 1 because it's a normal, right? So I do it for every value in this column, for everyone. And then sum the contribution of all of them. So if I have many points here in my sample, I will have many Gaussians here. If I sum them and divide by the number of samples, I end up with something which resembles the histogram, but which is continuous. That's a kernel density estimate. Okay? And if you put here too small a Gaussian, too narrow a Gaussian, your estimate of the density will be noisy. Okay? If the size of the kernel, if the size of the Gaussian is very wide, you will probably end up with something like this. So choosing the right kernel size is a subject of debate, and you can find thousands, or if not tens of thousands of papers on how is the best way to define your kernel size. Okay? So that's what I did here. I'm just representing kind of a histogram of the values that I find in my chain, but instead of putting them into bins, I do something smoother with the kernel density estimate. Okay? And the value I'm getting is close to 120. Now, I dare you try to do exactly, of course, with this you can actually do any representation. You could do it two-dimensional. Okay? You could do a kernel density estimate with beta and F, with T star and T disk. Okay? And this thing here integrates to 1. So you can do it two-dimensional. If you're very good at plotting, you can go three-dimensional, working with opacity and stuff like that, if you're able to interpret these kind of things. But anyway, so I one of the things I was going to propose was to run exactly the same experiment, but instead of fixing here the variance at 10 to the minus 6, put something much, much smaller, like 10 to the minus 12. That is, underestimate the variance of your offsets. Or even, if you want, go much smaller, 10 to the minus 60, for example. This is, in terms of numerical precision, this is entirely equivalent to removing the offsets. All the offsets will be 0. And try to infer the parameters of your disk, which we know because we've got sitting on the cloud. Try to infer them without assuming you have offsets. And the values you will get are wrong, are just wrong. Okay, you have very small value of beta, and the value of the temperature of the disk is also below 100. Okay, so this is one example where a model that fails to incorporate all that you know about the process of how your data were generated results in wrong inferences. It's extremely important that you try to incorporate in your likelihood everything that you think is taking part in the data generation process. Even if you don't know the exact value of how it was generated. In this case, even if you don't know this and try to infer it as part of the process, you end up finding, in this case, the right solution. What will happen if you try to, so in this case, if you try to infer the distribution where your offset come from with another prior, is that your distribution for, in this case, the temperature of the disk, it may be like this if you put this value of 10 to the minus 6, and it may be broader if you also infer this variance. Okay, so the more parameters you put in, the fuzzier the result is for your inference, because you are incorporating more and more uncertainties. In this case, we would be incorporating the fact that we don't know how are the offsets distributed. But that still is much better than neglecting the fact that you have offsets. If you neglect the fact that you have offsets, you end up drawing the wrong conclusion. Okay, simply because your model was not accurately describing the process by which the data were generated. So I hope I've convinced you that it's good to have these nuisance parameters, and it's good to actually go hierarchical. I will give you one last example before I move on to model selection of how we can use these hierarchical models. One way in which, in astronomy, hierarchical models come up naturally is the existence of initial functions, like the initial mass function. But they are everywhere in astronomy. Think, for example, about the problem of exoplanets. One of the questions that are very often asked by people in this field.
Listen, why do you think or know that somehow the offsets have a preferential direction?
Instead of using a normal probability distribution. So if you think that it's more likely that you have a positive offset than a negative one, you can use an exponential. So imagine, for example, the question that is often asked by people working in the world of exoplanets, like, what are the properties of the stars that have planets around them? Do planets form preferentially around stars in the G region, spectral type? Do we have more exoplanets around G stars than around M stars, or around F stars, A stars? How about the eccentricities? What's the distribution of eccentricities in exoplanets. There is a beautiful paper by David Hogg exactly on this, showing the importance of hierarchical models for going from raw observations up to these initial distributions, like the eccentricity distribution. I may have just one radial velocity, right? And from this radial velocity, I can compute the posterior for the eccentricity. That's the posterior for one system, right? I have one radial velocity, one star, I get the posterior for the eccentricity of the planet. Now, what if I have 100 or 200 exoplanets and the corresponding radial velocities? I can try to go up and try to infer the histogram of eccentricities, right? You can do it with an histogram, or you can use an analytic model. Let's suppose that I think that the eccentricities are distributed as a power law. It's not the case, but it could be, or whatever. So this is one way in which hierarchical models come up naturally in astronomy. We want to do histograms of the properties of individual objects. Now, the example that I prepared for this lecture is again synthetic. This is like working with a net below. So because my data are synthetic, I know what they should be, so it's easier for me to debug. What I've done here is to generate the beta values from an exponential distribution. So if you look here, originally I wanted to do it from power law, but I found it more difficult. It took me ages to debug, etc. So I finally ended up with an exponential. And the exponential has an exponent of 2.35. Just sort of like that. Okay. So I'm going to generate a number of SEDs, which is set to 50. I'm going to generate 50 spectral energy distributions. Okay. Each one coming from a different object. For each one of them, I will generate a temperature of the star, a temperature of the disk, a value of beta, and a value of f. I'm not using offsets here. I'm going one step back and simplifying the problem. Okay? And the values of beta will be generated from this distribution. With a scale parameter equal to 2.35. Okay? So from this distribution, I can sample. Of course, most of the betas in these 50 SEDs will be generated from low values of beta, because it's more probable here, right? This is a probability. So what I'm assuming here is that the values of beta in my populations are not random, uniformly distributed, cannot be anything between 0 and 4, which is the range I've been assuming in the past, but there is a structure there. And some values of beta are more probable than others. And I'm going to try to find out how does this law looks like. What is the scale parameter? There's only one parameter for an exponential decay. That parameter is the scale parameter. So I think I'm God sitting on the cloud. I know the alpha here is 2.35. And I am trying to see if I can actually recover this value. Okay? So my model here is the same as before, only I'm removing the offsets. And I'm assuming that the beta value comes from a prior, and this prior is a function of alpha. And I'm putting yet another prior on alpha. I'm going hierarchical, okay? I'm going hierarchical. Okay, so I generate the SEDs. You can see it here in this loop. Okay, so the number of SEDs up there is set to 50. For each one of them, I generate a random temperature for the star, a random temperature for the disk, a random value of beta sampled from the exponential. Sorry, I just realized that I didn't use alpha equal to 2.35. I used 1. I'm glad because I know that the outcome is alpha equal 1. So I was wondering, why do I recover 1 if I put 2.35? Here I should have written 2, I should have written alpha. Sorry, okay? If you put alpha, you will get the same. F is sampled from a uniform distribution, again in a very narrow regime because the uniform distribution here is not very appropriate. And then I compute the SED. The SED now is a matrix which has 50 rows, 1 for each SED I'm synthesizing, and I think it's 24 columns, 1 for each measured flux. Okay? If you plot the histograms of beta that you obtain, you get something like this. Instead of a histogram, I would have done a kernel density estimate. This is showing you that even though it was drawn from an exponential, the factor that we have a limited sample of this random variable is telling you that you may have deviations from the original distribution. So the line should go like this. We should have more bins, more values of beta in this bin, probably less in this bin, and this value is highly unlikely. Okay, so just we're drawing from a distribution that these things may happen. Don't be surprised. It's like if you toss your coin 6 times, you may get 6 heads. And the inference that you're going to make is going to be, of course, and you want it to be influenced by the data. If you happen to obtain a very improbable data set, then your inference will not be centered at the right value. That's life. Okay? So let's go hierarchical, and going hierarchical with Stan is very easy. It took me like 5 minutes to write this model in Stan because it's exactly the same as before, only I removed everything that had to do with the offsets. There's no offset anymore. And now, instead of specifying a prior for beta, which was uniform between 0 and 4, okay, if you go back to the previous model, the prior for beta was uniform, just like the other ones. The thing that changes is here. We had here beta sampled from a uniform between 0 and 4. Now I write beta comes from an exponential with a scale parameter of alpha, and the value I'm giving as input here is 1, 2.35.
There was no physical reason why you got why you sacrificed the alphas, the offsets of the beta.
No. Simplicity. Yeah, try not to mix things together. So actually there is no reason why the beta should be drawn from an exponential. I was planning to do it with an initial class function, with a power law, with an exponent, but it didn't fit so well into this. I had to complicate things far too much. So all the rest is the same. I only changed the prior for beta, and I also introduced here one line that says that alpha comes from a uniform distribution between 0 and 2. So it's this prior here. Okay? It's this prior here. As it turns out, it's not problematic to specify here a uniform prior. We are here in the case where 50 SEDs are enough to erase the information in the prior. And the upper, it's not completely erased, but the posterior is dominated by the library. Okay? But you can think, hey, this guy is teaching us statistics, and he's using the most simple, most silly prior. Then you're right. Okay? So what I would do, if I had to publish this in a paper, is to try several priors. I would not go to these very long priors that take 10 pages long, analytical priors, difficult to compute. No, I wouldn't do that. But I would try something coming from exponential, a beta function, something like that, and see what difference it makes in my inferences. Okay? So we do exactly the same. We define an initial solution, like here. Okay? And I'm playing a little bit of a trick here. because I'm actually starting at the right value. I shouldn't do this. I shouldn't do this. This is plain trick. This was changed, and I'm now starting my chain from the right value, right? So convergence will be very, very fast, okay? So this is a trick. If you please change it, there shouldn't be no problem. I'll keep my fingers crossed. But if you do change it and start from a value which is not the correct one, you should get still good results. Now I do the same as before. I extract fit and plot the marginal probability for alpha, for the length, for the scale of my exponential decay. Okay? Now the real value from which the data were generated was 1. And this is my posterior distribution. Okay? It's 50 SEDs. I think it is a wonderful exercise before you actually analyze real data to do simulations, because they help you understand in what regime you are. So I would say that in this regime, if I do this for these 50, another 50, another 50, another 50, another 50, I can get an idea of what would be the distribution of my maximum a posteriori, if you want to use a maximum a posteriori, for a sample size of 50 SEDs with 24 observations, okay? And you can try to do it instead of 50 for 200 or 1,000. And see, of course, the more SEDs you have, the better your estimate will be, right? If you, instead of 24 flux measurements, we have 50 or 100, we would probably have a narrower distribution. Why? Because each of the 50 SEDs would have a narrower posterior. Okay? So the uncertainties you are propagating are smaller. And therefore, the uncertainty in the upper level of the hierarchy will be smaller. So I don't think you would improve your posterior on alpha by measuring more fluxes for each star. You need more stars. Okay, you follow this argument?